Hello everyone. So we are done with chapter 14 last time. So we're going to have chapter 15 today, which we have started last time. We started with chapter 15 as acids and bases, and we said about the differences between the two acids and bases in terms of their physical properties. One sour in taste, while the other one is bitter in taste. One reacting with metals to produce hydrogen, okay? And we also have the definition of what we call acids and bases in terms of arrhenius acid, arrhenius base. So we could say this chapter has a lot of concept uh, where we can get a lot of questions for your second exam. So arrhenius acid is anything that gives up a hydrogen or hydronium ion, while arrhenius base is one that gives up hydroxide when dissolved in water. And then we also have the Bronsted-Lowry definition of the acids and bases, wherein we said that Bronsted-Lowry acid is one that donates hydrogen, while a Bronsted-Lowry base is one that donates or accepts the hydrogen or proton. Okay, and we say that if one loses a hydrogen or donates a hydrogen, the resulting product is its conjugate base. And if one, okay, that accept the hydrogen, the resulting product is its conjugate acid. Okay, and then we also discuss about some species that can act both as an acid and a base depending on what the other species that they have, and we call this amphiprotic or amphoteric species. And we also discuss about the Lewis concept of the acids and base when we say acids are electron pair uh, acceptor, while a Lewis base is an electron pair donor. So those are, we could say, rich source of concept questions that you might have for your second exam. Okay, so if you want to know what are the possible questions, so you can expect question: what is the conjugate acid of this species? What is the conjugate base of this species? Okay, which of the following is an acid? Which of the following is a base? Or the one that the question that we call challenging on our part but confusing on your part is which of the following statement is R or true? Okay, and then you're given their three statements, and then the choices that you have is A, one only, B, two only, three, C, three only, and then one and two, one and three, or one, two, and three. So those are the type of questions that you can expect. Now, the next thing that we're going to do is the so-called relative strengths of the acids and bases. So before we go to the relative strengths of the acids and bases, I think the first thing that we need to know is how do we define the strength of the acid? So what are those so-called strong acids and strong base compared with the so-called weak acids and weak base? So anyone remember chapter 4 in your what we call Gen Chem 1? How do you define a strong acid? Anyone? Okay.
If it was one, either in group 1 or 2.
Okay. So when we say strong acids, it's an all or nothing stop. So when we say strong acids, there's what? 100% dissociation. So when you have a strong acid, another way to explain their behavior is they are similar to the so-called salts, right? So if you have NaCl in water, what will happen? They will dissociate a sodium ion and chloride ion. Now, if you have HCl, which is a strong acid, they dissociate as H plus and Cl minus. Are they the same? What can you say about the difference between the two, NaCl and HCl? Anyone? One is an ionic compound and the other one is a covalent compound. But if you put them in water, both of them dissociate into ions. Okay? This due to its nature of being strong electrolyte and an ionic salt, and this one due to its nature of being a strong acids. So if you have a strong acids, it will dissociate 100%. And the good thing with the strong acids, you only have 6 to 7 strong acids. Anyone can give the magnificent 7 of a strong acids? So HCl is 1, HI, HBr, HNO3, H2SO4, HClO4, and in some book, HClO3. Now, all you need to know is know these 7 acids, and anything that is not listed there, automatically they are weak acid. Okay? Now, the same thing with the base. The base would undergo 100% dissociation. And the strong bases are the soluble hydroxides of group 1A and 2A. Sodium hydroxide, lithium hydroxide, potassium hydroxide, barium hydroxide, all of them are strong bases. Now, the weak bases are the one that dissociate less than 100%. Okay? So that's the thing that you need to remember, because you might have a question, which of the following is a strong acid, which of the following is a weak acid. Now, the odd thing about here is how come HF is not a strong acid? HF has a unique property. Okay? What's the unique property of HF? It can dissolve glass. Aside from glass, what else can it dissolve? Anyone? The good thing with the HF is it can dissolve glass, but you can put it in plastic. Okay? And I ask you, what else it can dissolve? So I don't know if you know the series Breaking Bad. So when the high school teacher there, high school chemistry teacher there turned Heisenberg, okay, or Heisenberg, okay, they tried to dissolve the body, or we could say the dead body. And what is his instruction to Pinkman? You go to Home Depot and you buy a big plastic bin. But what happened? Where did the guy put the body? And pour it with hydrofluoric acid. Anyone who watched the series? What happened? Okay, he was not able to buy the plastic bin, so he put the cadaver in a bathtub. And what happened after some time? Okay, the bathtub fell out of the house. Because what happened there is the HF dissolved both the body and the bathtub, which is made up of what? Ceramic material. So that's the thing here. That's the unique property of hydrochloric acid. Okay. So what does it tells us now about how strong acid, strong base, weak acid, and weak base react? So if you're going to look at this reaction, what can you say? The reaction that I encircle here is just like the name of the band. It's one direction. Why did I put it like that? Because if you have a reaction of a weak acid, okay, so what happened? Most likely, it's going to be a one direction complete reaction. So the one that is favored is always 100% from the reactant to the product side or the forward reaction. Because what happened here, if you put it, the total reaction that we have it, this is how it looks like. So what is the conjugate base of HCl? Anyone? In the given reaction, what is the conjugate base of HCl? Anyone? So if I ask the question in a multiple choice quiz or test, what is the conjugate of HCl in the given reaction? So what are you going to answer? A, B, C, or D? Anyone?
Would it be D?
Okay, so the answer would be
Yeah.
Cl minus. Okay, now what does this mean? The stronger the acid, the weaker its conjugate base. So remember what happened if we going to reverse the reaction. So if we have a reaction like this, so we assign this as what? This is the acid, this is the base, this is the conjugate acid, and this is the conjugate base. So what is the competing reaction that we have here? So we say one reaction that we have is HCl reacting with water. So what will compete with that reaction? Anyone? So I hope that mobile is not for you or for any one of you. Okay. So what is the competing reaction that you have here? So the competing reaction that you have is the H3O plus reacting with Cl minus. Now, because of the strength, so they say here, so this is what? And a strong acid, so this will be its conjugate base. So in terms of what we call the strength, this will be weaker compared to the base that you have here. Now, in addition, the conjugate acid that you have here, this will be also weaker than the HCl that you have. So what does it mean? The forward and the backward reaction are competing with one another. Now, who will win? In a competition, who always win? In the competition of strength, who always win? Huh? It's always the strongest, right? If you watch the old Mortal Kombat movie, your soul is mine. Okay? So the same thing that we have here, the stronger the acid or the stronger the base, the most likely it will be the one that will be favored. So between HCl and H3O plus, which are both competing as an acid, So HCl is a strong acid. So the one that is favored is this one. Okay? So the weaker an acid here, the stronger its conjugate base. So this is your acid. So it's a weak one. So its conjugate basis of that is this one. So it's a stronger one. So both the stronger acid and the stronger base are on this side. So it will favor the forward reaction. Okay? Now, as a guide to you in terms of the strength that we have here, we have a table. So what can you say? HClO4, H2CSO4, HI, HBr, HCl, HNO3. So those are what? Those are the strongest acid. However, its conjugate base are the weakest. Because it's just like if you are strong in one side, your other side will be weaker. And if you are weak on one side, the other side will be stronger. So I asked you about HCl and H3O plus. So as you could see here, HCl is stronger than H3O plus. So if you have a competing reaction where in one side you have HCl, on the other side you have H3O plus, the one that has the HCl, which is a stronger acid, that's the one that will dictate the reaction. Okay? Now the question now is, what if they're both weak? Like the next one here. So formic acid is a stronger acid than acetic acid. So which is the stronger base? Formate ion or acetate ion? So what can you say about the relationship between these two in terms of what? Stronger base. So you're familiar with acetic acid, right? You can find acetic acid in what?
Vinegar.
Vinegar. Okay. Now how about formic acid? Do you think you encounter it already? Juice? Hmm. Juice is usually citric acid. You encounter formic acid, okay, if you're bitten by ants. Because it was named by what they excreted. That's formic acid. Okay, because the scientific name of ant. Anyone taking bio? What's the scientific name of ant? Anyone? You have a bio that is like a systematic bio that you have, right? So the name of ant is Formica rufus. So that's where you get your formic acid name. Is that how you write the scientific name? I'm not a bio, so I'm not sure if that's the way to write it. Okay, but that's the thing that we have. So it says here, your formic acid is stronger than acetic acid. So how is the strength of the conjugate base of the two?
Is the acetate ion stronger than the formate ion?
Okay, so we could say they might do it like this. Since this one is stronger than this one as an acid, So the conjugate base that it formed will be weaker than the one that is a weaker acid. Do you get that concept? That if you are strong on one side, your conjugate base will be weaker on the other side. Or if you are weak as an acid on the reactant side, your conjugate base will be stronger, okay, on the other side. Now, you ask yourself, how do we know why this one is stronger than this one, this one, this one, this one? Or we could say, what is the factors that affect the strength? So that you don't need to memorize the table that I have shown to you. So the answer is this one there. The acetate ion is a stronger conjugate base compared to the formate ion. That's the answer. Now, let's try to look at some of the factors that affect the strength of the acid. So the first thing that we're going to look is the molecular structure. So what does it mean? So when we're talking about acid, what's the element that is involved? Okay, it's just a proton, or specifically hydrogen ion. So they said the strength of the acid depends on how easily the proton is lost or removed, dissociate. So they want the hydrogen to be give up easily. Okay, so the easier for it to be give up, the stronger the acid. Now, the thing that we can look is the more polarized the bond between hydrogen and the atom to which it is bonded, the more easily the hydrogen is lost or donated. So, polarized. So what does it mean by polarized? The more polar the substance is, okay? The more that they have the partially positive and the partially negative, and the easier for it for the hydrogen to be dissociate. So let's look at the binary acid. So when we're talking about binary acid, it's made up of hydrogen and another element. So they said here for a binary acid, as the size of the X in HX increases, going down the group, the acid strength increases. So what does it mean? Let's look at the table that we have here. So the one that is most stronger, Hi, stronger than HBr, stronger than HCl. Does that make sense in the trends that we have? Is iodine the one found in the lowest part of the group? So we have here Hi, HBr, HCl. So what could be the reason here? Why is it the bigger the molecule, the stronger the acid? So what do you know about the strength in your periodic table discussion in Gen Chem 1? The smaller the molecule, okay, the most likely it has a strong attachment with your hydrogen. So what happened? If you have a stronger attachment with the hydrogen, hydrogen will not dissociate right away. Unlike if you have a bigger atom, okay? So the bigger the atom, most likely the interaction that atom has with the hydrogen is not strong compared as the smaller atom. So what will happen is it's easier for that bigger atom, okay, to have its hydrogen dissociate. Hence, you have a stronger acid. Is that clear? Do you get the explanation why the size affects the strength? So the smaller the atom, so most likely they will interact with the hydrogen that we have. So if they interact, it's not easy for the hydrogen to leave. But the bigger the atom, is just if you look at the discussion that we have in the bigger atom, usually it doesn't connect with the outermost electron. So it doesn't have an interaction with the outermost electron. What more with another atom? So that's the explanation that we have here. Now, for within a period, if you're going to look at it, like going from left to right or across a period, as the electronegativity increases, acid strength increases. How do we explain this? What is electronegativity? From left to right. This is from left to right, huh? This one is top to bottom. So what happened to electronegativity from left to right? Will it go up or go down?
Doesn't it increase? Does it increase?
Okay. So from left to right, electronegativity increases. Okay. So you can only apply electronegativity when you're comparing atom from left to right, because if you're comparing atom from top to bottom, the size is the one that is more important. But it is from left to right. Okay. So you look at it in terms of electronegativity, and it says there, acid strength increases. So if you have the, what's the one beside HCl? Is it HS, H2S? Like in HF, the one beside it, if I'm not mistaken, is H2O, right? So between the two, this is a stronger acid compared to this one. Between these two, this is a stronger acid compared to this one. And the explanation that they have there is in terms of electronegativity. Okay, so let's try to ask some questions, because these are most of the questions that may come out in your second exam. So which is a stronger acid? HF, HCl. So maybe so that we can have a participation, you have a reaction there, right? Either you do it like this, or what's the other one? The hand. So this is the thumbs up, and this is the clap. So which is a stronger acid? Maybe you answer it whether you have thumbs up or clap. Trying to look at the other one. So I have some hand. Okay. I think I see most of you with the hand. So the answer there is the hand. Okay. It's the HCl. So using the same thing, which is a stronger acid, water or H2S? Oh, yeah, they're both them. So one is clapping and one is thumbs up. Okay. So between H2O and H2S, so the main way to compare them is through this what we call location that we have. So one is lower compared to the other one. So hydrogen sulfide is the one that is stronger. How about HCl or H2S? Is it the clap for the H2S or the thumbs up for the HCl? Okay, so the answer there is thumbs up. Your HCl is more stronger than H2S. So do you think you can answer it? in the exam? Question like that? Now, how about the one that deals with what we call the oxo? What are the factors that we need to consider? So when we have an oxo, we have there an oxygen attached usually to a halide, okay, and attached to hydrogen. Hydrogen should always be there in your what we call acid. So for oxoacid, several factors are relevant. The number and the bonding of your oxygens, the central element, and the charge of the species. So for a series of an oxoacid, you always have it like this. OHM, YO, N. Acid strength increases as N increases. So what is N here? So usually the N here is the attachment that it has to your what we call the number of oxygen. So if you have HClO, so the way that you have to do it is like that. And then HClO2, HClO3, and HClO4. They just separate this one to tell you, okay, that the Y is attached to the O. And they're also attached to a hydrogen that is attached to an O. So based on this one, acid strength increases as the number of oxygen increases. So HClO3 is the strongest among the four of them, followed by HClO4, followed by HClO3, followed by HClO2, and the last but not the least is HClO. And I don't know if you're familiar what is ClO minus. Are you familiar with ClO minus? Some of you are doing that. It has a distinct smell. Anyone? Have you done laundry already? So what is the ClO minus in your laundry? That is your, anyone?
Chlorine? Chloride?
Bleach.
Bleach?
Yeah, isn't it bleach contain chlorine? So that's the one that you have in your bleach, not the anime bleach, okay? So this is the bleach that you use to whiten your clothes. I don't know if you know it, but you don't use bleach for colored shirt. Am I right? What you do is oxidize any of the dirt that you have in white clothes. Now, another thing that we can look at it, so we said that the more O that you have there, the stronger the acid. So another thing that we have to know is the Y element, the halide element. So why do we say this is stronger compared to this one? Why is the chlorine or the HClO is stronger compared to the HBRO? So they said it has something to do with the electronegativity of Y. Okay? So what does electronegativity do here? So what it do? So as you could see here, Cl is not connected directly to H. The one that connects the two is an oxygen. So what happened here in terms of electronegativity, chloride, okay, being more electronegative than bromine, it pulled the oxygen towards itself. So if that happened, you have what? Electron being negative charge, you have your partially negative end. And since there's a strong interaction that they have there, because chlorine is more electronegativity, more electronegative than bromine, okay, it's easier for the hydrogen to dissociate. It's just like chlorine asking the oxygen, "You're mine. I don't know who are you attached with." So if the electronegativity there makes the what we call the pulling of oxygen towards chlorine. So when it happens that, it's easier for the hydrogen to leave. Compare it when you have the bromine. The electronegativity negativity of bromine is not as high as the one that you have in the chlorine. Okay, now the last basis that we have to determine the acid strength is if we have the so-called polyprotic acid. And its anions decreases with increasing negative charge. So what does it mean? Okay, the more hydrogen that you have, the greater is the acidic strength. So H2SO4, carbonic acid is always stronger than bicarbonate. Sulfuric acid, which is a strong acid, is much stronger than HSO4 minus. Phosphoric acid is much stronger than dihydrogen phosphate. And dihydrogen phosphate is a stronger acid than monohydrogen phosphate. Okay, so that's what it means. That's the basis on how you do or determine the strength. And knowing that knowledge that you have, we go back to the example that we have before. A reaction will always go in the direction from the stronger acid to the weaker acid, and from stronger base to a weaker base. So it's not only in real life that the strong ones are dominating. Even in the chemical world, okay, the strong acids and the strong base will be the one dictating the direction of the reaction. And that's the direction of which the strong acids and base, right, are in the reactant side. So let's try to look at this one. So decide which species are favored at the completion of the following reaction. So what I want you to do now is identify the acid on both sides. And then I'm going to bring you to the table, okay, that determines their strength. So you have to identify which of these two is stronger, an HCN or an H2SO3. So this is sulfurous, not sulfuric acid, sulfurous acid. So now that you have that, we'll go to our table and try to determine where they are.
H2SO3 is higher than HCN, so it's the stronger acid.
Okay, so as you could see here, it's a choice between this one and that one. So if you're asked here, which reaction is favored, what was your answer?
The reactant.
Is it going to, is it the backward or the forward reaction that is favored? So since this one is stronger than the other one, so we could say it favors towards the reactant.
What is that? Oh.
Okay? Question. Before we go with another KW or another K, the KW. So what is unique with water? In biology, water is what? If you know your biology, Earth is made up mostly of what? Water. If you go to anatomy, human anatomy, human beings are mostly made up of water, right? So if they will find water in Mars, America will invade Mars. Okay, because that means they can sustain life there in Mars. So in the chemical world, water is unique because it can act as an acid or a base. So if you have two molecules of water, okay, one can act as an acid, okay, one can act as a base. So one that acts as an acid would gives one of its hydrogen, and the other one would accept its hydrogen. So you have their form an H3O plus, which is the conjugate acid of the base, and a conjugate base, which is OH minus coming from H2O. In some, they just put it like this, water, okay, dissociating itself to give you what? H plus and OH minus. They're just the same. Okay, whether you have two molecules of water or a molecule of waters dissociate to give you an acid and a base. Now, what's unique with this one? So if you're going to write the reaction here, so H2O in liquid plus H2O in liquid, you produce H3O plus and OH minus. That both are what we call aqueous in nature. So if you're going to write the law of mass action, you will write it like this, right? But as you could see, what can we say about the water? It is, what do we say if we have liquid or solid in the equilibrium expression? They are what? Anyone? They are constant. So what you do, you incorporate that with the Kc. So Kw is really what? Kc times H2O squared. Okay? So they just become the so-called Kw. And they found out at 25 degrees Celsius, the value of your Kw is 1.0 times 10 to the negative 4. So Kw is just the product of hydronium ion and hydroxide. And as temperature increases, the value of your Kw also increases. Now, in this chapter, we're going to get, okay, we're going to deal with what we call strong acids and strong base. And we have already a definition of a strong acid and a strong base. Okay? And the way that we look at these strong acids and strong base, we just look at the concentration of the hydronium ion or the hydroxide ion. So if we're going to calculate here, the hydronium and the hydroxide ion concentration, let's say for this one and this one, how do we do it? What is H plus equals to here? Anyone? What is H plus equal to? Okay, so what if you're not sure, you have HCl. What happened to the HCl? It will dissociate to give you H plus and Cl minus. And based on the concentration, you have 0.1 And here, it will also give you 0.1 and 0.1. So the H plus, at least for this one, is
0.1 M.
0.1 molar. So this is the easy one. Okay. Now, how about the magnesium hydroxide? Which one are we going to measure there? So magnesium hydroxide will give you magnesium 2 plus and 2 hydroxide. So that means for every 1.4 times 10 to the negative 4, you will have here 1.4 times 10 to the negative 4. And you have here 1.4 times 10 to the negative 4 times 2. So this is equals to hydroxide 2.8 times 10 to the negative 4 molar. And based on the concentration of your hydroxide and hydronium ion, you can predict whether you have an acidic solution, a neutral solution, or a basic solution. What do you think is the basis that you have there? So you have here Kw equals to what? H3O plus times OH minus. So what's the value of Kw that we have there? At 25 degrees Celsius, you have 1.4 times 10, 1.0 times 10 to the 14 negative. So what does it mean? If we have that value, we can determine the value of our H3O plus and OH minus. So let them equals to X. So what will be the value of X? Because this one, X times X will give you X squared. So X squared is equals to 1.0 times 10 to the negative 14. So if you're going to get the X of that, that is just equals to the square root of 1.0 times 10 to the negative 14. So what is that equals to? Anyone? It equals to this value. Because I'm just showing you where the hell the 1.0 times 10 to the negative 7 came from. So that's where it came from. So when you have a neutral, both the concentration of the H3O plus is the same as the concentration of the hydroxide. If the concentration is higher than 1.0 times 7 for the H3O plus, then you have an acidic solution. If the concentration of the hydroxide is greater than 1.0 times 10 to the negative 7, then you have a basic solution. Because as you could see here, all of them are what? Hydronium ion. So what can you say about the hydroxide ion? For the acidic, your hydroxide ion is less than 1.0 times 10 to the negative 7. And later on, we will simplify that what we call way of determining whether it's acidic, basic, or neutral. But if we're going to look at the molecular view on how they look like, okay, so usually this is how they will look like. So you will be asked here, rank the following solution from the most acidic to most basic. Water molecules have been emitted for clarity. So the one that you have there is just either H3O plus or hydroxide. So if it's acidic, that means there's more hydronium ion compared to hydroxide. If it's the other way around, then it is basic. If the number are the same, then it is neutral. So the first one, if you're going to look at this, I have 1, 2, 3, 4, 5 hydronium ion and 5 hydroxide. So that's neutral. Now for the second one, I have 1, 2, 3, 4, 5, 6, 7 hydronium ion. So only 3 hydroxide, so it is acidic. Now for the last one, I only have 1, 2, 3 hydronium ion. So there are more hydroxide on it than it is what we call basic. Is that clear? Now to simplify this one, they adopted this concept of pH. So if we're going to list it from most acidic to basic, it's BAC. So they said pH is just negative log of hydronium ion. Now, where do you think the pH was developed? Anyone? This concept of what we call pH, it's a product not from the academe like universities, but it came from an industry. What do you think the industry where it came from? What industry was the concept of the pH was used first, and then when the academe got hold of it, they said, oh, this is a new, a simple way to determine the pH. Hint, it came from a food industry. So the question now is, what food was this measurement of pH came from? Anyone? Any guess? If you're fond of food, did it came from McDonald's? Did it came from Popeyes? Okay, where do you think it came from?
Alcohol.
Okay, very good, Karin. It came from alcohol. It came from Denmark. I don't know if they still exist, but when I was young, I usually watched their commercial, Carlsberg, probably the best beer in the world. Okay, so there's a scientist that that they have there by the name of Sorensen. Okay, and what he did is he found out that if he monitored the quality of beer using this pH, he can find the best quality by just knowing the pH. So he wants all the workers that she had there in the brewery to maintain that pH because that's the best quality of the beer that they have. Okay, so pH is a product of what we call the industry. And I hope you're familiar with your calculator because you need the calculator here. pH is just equals to the negative log of H3O plus. And later on, you will see that pH is not the only one that you can use to determine the pH of the solution. So the way that you look at this, what we call pH, okay, only the decimal part of the number has significant figures. The whole number part called the characteristic is not significant. So there's also a rule that you have here. Okay, so let's look at the simple calculation for pH. So calculate the pH of a typical adult blood which has a hydronium ion concentration of 4.0 times 10 to the negative 8. So how do you do that? So pH is equals to negative log H plus or H3O plus. So it's just negative log. You substitute the given number and then go to your calculator and then do the calculation. So that is equals to what? 7.40. Now, this is where I want you to remember where the significant figures is. How many significant figures is this number has? Does this number have? Anyone? How many significant figures do you see here in this number? Okay, because I might give the choices here in the multiple choice like this. I have class. Ask Kuya. So, which do you think is the correct answer here? Okay. So, in the previous slide, it says there, the whole number part called the characteristic is not significant. For a log, only the decimal part of the number has significant figures. So what does it mean? You have two significant figures here. So your final answer here, there should be 2 decimal place because that's the only one that is significant. So if I'm going to give you a question like this, if you answer anything at this, don't expect it to be right because the only one that's right here is the first one. Is that clear? So that's how you use significant figure if you have a pH. Now, if you're given a pH like this, and you are asked for the concentration, so this only has 2 significant figures. So your concentration should be written also into significant figures. Now, aside from the pH, okay, we can also have POH. And the POH is just the negative log of your hydroxide. And what we know, pH plus POH will give you 14. Now, the question is, how about if the one that is given is the pH and you want to get the concentration of the hydronium ion? Can you get it? Yes. All you need to do is what? 10 raised to the negative pH. So usually in the calculator, that is the inverse of log. So I don't know what calculator you have, but oh no, cannot detect. I have to remove my virtual background. So if you're going to look at this, so see that log, where's that log? There. So the inverse of log is 10 raised to the x. So it's not really clear. The one that you have here, the inverse of that. Okay. And if you want to get the concentration of the hydroxide, if you have what we call the POH, then you just use 10 raised to the negative POH. So let's see. Let's try to solve problem like this one. So these are the calculation problem that I like you to be what we call sure points in your exam. So the pH of natural rain is 5.60. Okay, what is its hydronium ion concentration? So if we're going to write it, it will just be H3O plus equals to 10 raised to the negative pH, which is 10 raised to the negative 5.60. So you have 2 significant figures here. So that is equals to what? I think you were able to answer the question. 2.5 times 10 to the negative 6. And I can assure you, if you mess up your calculation, the number that will come up with the calculation is also one of the choices that you have. So I want you to double check your answer. Okay. Just like what is that contest? Is that your final answer? So you should always ask yourself, is this the final answer? Okay. Because most likely, okay, the way I was trained when I'm doing the ACS exam, one of the choices that we usually put there is any number that will come out in the calculation if you bungled or mess up your calculation. Now, to end the chapter, this is the thing that you need to know. Once you're given one of them, you should be able to get the other three. Okay? So for instance, how do we go from H3O plus to OH minus? Or how do we go from H3O plus to pH? So usually, we can do it like this. Hydroxide is just equals to Kw, which is 1.0 times 10 to the negative 14 divided by H3O plus. Or we can get the H3O plus, wherein 1 times 10 to the negative 14 divided by the given hydroxide. I think the easier one is coming from here, going there, coming from here, going there. Okay? So if you're given the hydroxide, you want to get the POH, it's just the negative log. Right? If you're given the H3O plus, you are asked for the pH, it's just a negative log of H3O plus. If it's the other way around, it's just 10 raised to the negative pH or 10 raised to the negative POH. Now, if you have a pH going to POH, the sum of them will always be 14. So to get one, while the other is given, all you need to do is subtract it with 14. So let's try. If I have, let's say, a number here like 7.50. So what's the corresponding POH? What's the corresponding H3O plus? What's the corresponding hydroxide concentration that it has? Let's try before we end the chapter and proceed to the next one. So which one do you want? Which direction do you want? So from here going there, it is 3.2 times 10 to the negative 8. Instead of here going here, you can go here going to this one, and then from here going to that one. So what's POH? What's the POH? So 14 minus 7.50. So that is around what? 6.50? And then I can go from here going here or here going here. The number should always be the same. So what is the OH minus? So I think it's also 3.2, but times 10 to the -7. So what else do we need to remember here before we end this chapter and go to the next one? What's the relationship of pH with respect to H3O plus? What do you think is the relationship between the pH and the H3O plus? Anyone? What do you think is the relationship? As the concentration of H3O plus go up, what's happened to the pH? These are the type of questions that's going to be asked in your exam. Which of the following statements is or true? Anyone, what's the relationship between the two concepts here? As the concentration of the hydronium ion increases, what happened to the pH? Will it go up or down? Anyone? So the relationship that you go here, it will not go up. Okay, the relation that they have here is just like a seesaw. When the pH is low, what? The H3O plus is high. Okay, so I want you to get what is the hydronium concentration when the pH is equals to 1. And what's the hydronium concentration when the pH is equals to 2? pH to 1, I think you get this one, right? pH equals to 2, you get this one. Am I right? Am I right? So those are the stuff that you need to remember, because those are the type of questions that will come out. And please don't disappoint me. Because those are the sure points that we have. Okay? So that's what we have for chapter 15. Now, as you could see in chapter 15, we just tackle the strong acids. And you may ask yourself, where is the weak acid? Okay? So the weak acid is in the next chapter. I'm trying to share it. And look at the title that we have for chapter 16. It's a combination of chapter 15 and chapter 14. Acid-base equilibria. And I think, let's see if I can play the video.